My name's Stefan Trawicki. I'm a second-year PhD student at Lancaster University, and I'm also a machine learning engineer at MindGuard. So I'm presenting my work today, Compilation as a Defense, Enhancing DL Model Attack Robustness via Tensor Optimization, which is a mouthful, and I'll explain all the stages to it. Okay, so we've already had a very good talk this morning about adversarial machine learning. I'll briefly go over it again, some of the bits we do at MindGuard and some of the bits we research ourselves. So adversarial machine learning, it's a bit different to classical cybersecurity that a lot of you do. It's attacks on machine learning models and their systems, as well as like the data sets used to train them, the models, the GPUs that underpin them, frameworks that allow you to do machine learning. The whole environment of machine learning is covered under AML. So obviously, Professor Goldstein talked about inversion and evasion attacks. He showed us all those pictures of animals getting stolen and mangled and everything. And he didn't really talk about extraction, which is what we deal with, which is more or less when you have an ML model, like in an environment, you can leech certain bits out of it, like the parameters, its architecture, its training data. And then from that, you can use the data as you see fit. You can use it for espionage, adversarially. It's quite interesting. So internally at MindGuard, we kind of model the environment as you have like the highest level, which is the easiest to attack, which is the API layer, and then you gradually go down in all the little bits and pieces that support ML down all the way to the hardware, which is GPUs. So you can get attacked at any of these different layers in the ML stack, as we call it, and the area that I focus on primarily is hardware. So as I just said, we do AML side channel attacks. These are the ones on the hardware themselves. So AML side channel attacks, mostly extracting leaky information from running processes. So when you do machine learning, you can imagine you've got a GPU here, it's an A100 running ResNet 18, say. An adversary can, through different means, listen to your GPU, do some kind of reconstruction process, and on the other side, they can spit out whatever they've extracted. In this case, they've extracted the architecture of the model. And I've kind of indicated that maybe the architecture is imperfectly reproduced, but there we go. And the way this kind of works internally is adversaries associate data that they extract from your GPU with attributes of a model that you're running. So from ResNet, we've got some conv layers, some ReLU layers, and in the reconstruction, we can kind of figure out with signals from the GPU what layers have run, and then you can reconstruct it. So we kind of call this the fingerprint left by the resources when they're accessed and allocated. And there you go, you can extract sensitive or valuable information from them. There are risks associated with side channels. There is a threat model for them. The leaky information that you can get from a GPU with your little probes, it can come from many different things that are running during the ML lifecycle. So in the example I'm going to give, it's monitoring the kernels that are being executed on a GPU. But the kind of area that we're in at the moment, we don't really consider much of the data that's being used when training or optimizing a GPU as sensitive. So there's not really much security consideration paid to it. So there's lots of data floating around that we can use to find out different bits and pieces. Side channel attacks are also potentially model and dataset agnostic. So the attack that I do doesn't care about the dataset, doesn't care about the model. It kind of cares about the framework a little bit, but broadly it's quite agnostic. And they can undertake side channel attacks in very few inferences. So when I've been doing this, a single attack, an instance of an attack can take 0.6 seconds, like barely anything. And when you've got the architecture parameters or data from a model, you can also stage further attacks. So if you know the architecture of a model, you can then make it easier to attack at a later stage because you have some knowledge you didn't have before. So current defenses against side channel attacks like this, you can use standard cybersec methods to secure systems, but obviously it's a huge space. You're probably going to miss things. Yeah, they're classic cybersecurity problems. There are also other approaches out there. So there's one called model obfuscator that I've read about. You essentially get the architecture of your model. So we've got A on the left here, and then you can inject random nodes, random connections, etc., that don't impact the performance of the model, but they change it when it executes on the GPU, it looks different. It obscures and adds loops. It's not model or framework agnostic, so it requires a bit of engineering effort to port across to a new system. I think the model obfuscator paper actually used TensorFlow Lite, which I know not that many people use for development. And the fingerprint of the model can actually remain the same as before, because when you run through, when you do a forward propagation pass, you're still accessing the same nodes. So it doesn't really help that much. So what we'd really want is a method to agnostically modify both the architecture and the execution fingerprint. So the objective of my work is to use compilation as a defense to achieve this. So I'll talk about the compilers in a moment, but essentially we want to generate some bespoke operator implementations that look different on the GPU to kind of what the attack would be expecting. Yes, so basically making a fingerprint less readable as a byproduct of optimization. Optimization is still the end goal. We want to make the model faster, but can we also try and make the model more secure at the same time? And the whole kind of idea is to break the association between the model executing and the kind of process signature. And also, we'll have no negative impact on inference time, because the goal of compilation optimization is always to make the model execute faster. So it's kind of trying to have your cake and eat it, I suppose. So background on machine learning compilers, they're very similar to what you'd normally associate a compiler with. They're basically the same as, LLVM. When you write machine learning code, you're typically writing TensorFlow, PyTorch, etc. All they are is a graph representation that's mapped into executable code that runs on your machine. There's slight differences. Some are more declarative. Some are a bit more verbose. But really, they do the same thing. They even execute the same kernels when they run. So typically, with compilers, you have intermediate representations that are lowered to lower levels. So in the case of machine learning, you go from your nice graph that you write in TensorFlow, that's pushed down to a tuned intermediate representation. That's pushed down again into LLVM or NVCC, and that's pushed down again eventually into machine code that runs as a kernel on your GPU. And when you lower the intermediate representations, your code becomes less optimized unless there's kind of optimization stages put in. Whoops-a-daisy. Yes, so unless you put optimizations in, your code will run worse every time you lower an intermediate representation. And most compilers, like NVIDIA TensorRT, use heuristics. So this is like the classical school of compilers. These are hand-tuned optimization rules written by experts that are very good and they work quite well. And you have kind of heuristics that you can apply. You also have things like operator fusion. It's kind of hard to see on here, but say you had like 3 convolutions in a row, the compiler will look at that and go, nice, I'll just compile those into one big convolution instead. And the kind of other school of compilers is Apache TVM, which if you've never used it is a nightmare, but it's very, very cool. So essentially, instead of having an expert write an optimization rule for you, Apache TVM finds them, which is amazing. But it is very big and it's a large process to run. Essentially, like if you did it on Resonate 18, it is probably a much bigger process than just training the model. It's a very power-intensive process. But essentially, it uses simulated annealing to generate a set of optimizations that could potentially be applied to your model. And it applies them and it tests how well that runs on your machine. And then from that, it trains like a model to estimate the cost to run on your machine. So you don't have to test it every single time. But essentially, it guides its tuning towards certain sets of optimizations that run better on your hardware. So after like 500 iterations, you can go from a model taking 500 seconds to run to a model taking half a second to run. It's very cool. It's end-to-end. It accepts almost any front end, so TensorFlow, PyTorch, Onyx, anything. It optimizes both the flow graph, which is what I was showing here, and it optimizes the operators themselves. So it finds, whether you can use more efficient compute primitives that you have installed on your system. And it can target almost any backend. So a new GPU comes along, someone writes some code to make it work, and then there you go. This whole process works for a new GPU. It's fantastic. Yeah, so we're just leveraging a very mature ecosystem, basically. And essentially, my goal is apply TVM to different models in different domains, architectures, and sizes, and perform increasing amounts of optimization with more trials and different optimization tuners, and to assess whether the success of a side-channel adversarial machine learning attack decreases when you optimize your model. So to set up the experiment, I have Resonate 18, DenseNet 121, Roberta, and YOLO v4. They're 8 to 124 million parameters, so quite a wide set of model complexity. They're multi-domain, so there's some image classifiers, some text, some object detection. And they're all in the Onyx framework. Framework doesn't matter because TVM compiles them all to the same, it converts them to the same intermediate representation. So this would work with any framework that you wanted to make it work with. And then I tested by changing certain parameters in TVM. So between 0 and 500 trials, between the random and the XGB rank tuner. And I also tested with and without graph optimization, but I'll talk about that later. So it's about 240 combinations, 83 hours of compute. I'll cover the tuner and the trials in the next slide. So my assessment pipeline was going back to the diagram we had earlier. In my case, we're on an A100 GPU, running models in the Onyx runtime, measure some parameters, measure the processes using the NVIDIA NCU tool, and then with the output of the NVIDIA NCU tool, run that through the deep sniffer attack, and then reproduce the model at the end and see if the architectures match. So NVIDIA NCU is used to measure the kernel memory reads and writes, and then the attack that I've chosen to run is Deep Sniffer, which is a side channel attack that's been around for a while now. But essentially, it takes in a log of the memory reads and writes of a kernel, and then tries to, well, a set of kernels, and then tries to reconstruct the architecture of the model that ran them. So this attack doesn't read code. The only thing it takes as an input is the logs of the kernels that ran on the GPU. And the kind of success element of this is the reconstruction accuracy, also called fidelity. So if you had a reconstruction accuracy of 0 and you had ResNet 18 here, your reproduced model would look nothing like ResNet 18. But if it was a reconstruction accuracy of 1, ResNet 18 that came out of the reconstruction would look identical to the original. So preliminary results, the paper is a vast abstract, so I haven't got explanations for all the results, but I can cover kind of broad strokes. So ignoring Roberta for a second, we can see that from 0 trials down to 500, the fidelity of the attack decreased. So that means that over time, with more trials, the success of the attack went down. So this is using the XGB rank tuner, which is considered the better tuner of the ones I tested. See ResNet 18, especially YOLO. Actually, YOLO decreased by a lot over time. I think the biggest decrease was YOLO at 42%. And Roberta, to explain that, Roberta is a text classifier. It uses different operators to what Deep Sniffer was originally designed for. So we're under the impression that essentially Deep Sniffer, even with trials, can't do a very good job of recreating Roberta because it just doesn't know its operators as well. So that kind of explains that. But broadly, overall, success. And then with the random tuner, which is a less guided tuner that doesn't make as intelligent decisions about how to optimize your model, we can see that it also succeeded with trials, but that it converged at a slower rate. So if I go back and forth, XGB rank decreases a bit faster than random. And now I also have a discussion about a few of the bits and pieces that I've thought of while working on this and some other results that I got. So I also tested applying graph optimization. So if you imagine your architecture like ResNet 18, you can merge certain operators together, like 3 convolutions in a row can be put together, and then certain other operators, TVM will automatically merge. So when that is turned on and you modify the architecture of your graph, these are the results I get. So I didn't include these in the original paper. They probably need a bit more exploration to figure out what happened, but you can see as you apply more trials, the success of the attack actually goes up, which isn't good. And then as you do more and more trials, the success starts to come down again. And if we look at a higher resolution view with more trials at the bottom, we can see even weirder behavior where on YOLO v4, the attack success increased and then went down. But for other models, it kind of went up, went down, went up, went down again. Don't know what's going on. So a bit more work is needed. Another kind of thought I've had is instead of optimizing the entire model and trying to do the optimization process that can take hundreds of hours, it would be better if we found out which operators were kind of conducive to success of side channel attacks. So if, for example, this max pool here in the middle was found to be really important in the reconstruction process, we could just optimize that ridiculously and then leave the rest of the model to not be as well optimized. And perhaps that would be a better use of resources. I can also think of another way of improving this. So I've tested using auto TVM, which essentially you give it a template for what you want your operator to look like, and it will basically fill in the gaps and propose certain optimizations that improve the speed of your model. But answer, which is part of TVM, just forgoes having a template at all and finds even better optimizations. It's a bit more of an involved process, but it can find even better implementations than TVM can normally. So it would be interesting to give that test. And then obviously it'd be interesting to experiment with this in a more real world scenario where we just switch between optimizations continuously, see if having a moving target means that an adversary can't track you as well. And also, it's completely possible to apply this with existing approaches. So there's nothing in what I've done that you couldn't apply Model Obfuscator, the approach I talked about earlier, fully compatible because the compiler toolchain means that as long as you put in a legitimate model, what you'll get out is a legitimate model. So that's quite good. So to conclude, I've demonstrated an automatic and agnostic method to increase model robustness to side channel attack. We found that in the best case, the attack success decreases by more than 40% when you use tensor optimization. And I've also discussed avenues to expand the preliminary work. So thank you.
Excellent. Great talk. Let's take a few questions.
Hey, thanks for that talk. That was, yeah, this is something I've never thought about. I don't know that much about the hardware exploitation space. My question is, yeah, actually on this graph, I was wondering if you could comment on the initial fidelity that you see even with very few trials. I don't know how meaningful it is like to be at 0.15, but it seems like not that high. So I guess my question is like, how successful can these reconstructions be using this tooling without any of the mitigations you're describing?
Sure. So I should really say the actual absolute value of the reconstruction is not too relevant. So when I've been testing with Deep Sniffer, the attack that I ran on this to get these results is a few years old at this point. The reason I used it is because it works just kind of out of the box. It works with our hardware. It's quite reliable. It's a good attack. But when it was made, it was built more for ResNet 18 and like YOLO, and Roberta, it obviously has no clue. And also Deep Sniffer originally was built for PyTorch. It wasn't built to be used with TVM. It just so happens to work reasonably well. From our testing previously, we've seen the relationship we see here with the values decreasing. It is the same kind of relationship between PyTorch and Onyx. It's just that Onyx has kind of lower absolute values because it was never trained for it. But the actual relation does hold. So when we've run Deep Sniffer before, we've seen fidelities of like 65, 70%. So kind of just by bringing it into a different language like that TVM has on the device, it immediately decreases the fidelity. But you would obviously make the assumption that an attacker could account for that. They would possibly test on different frameworks and things like that. So yeah, it's not the absolute value that matters as much. It's the relative decreases on each stage.
Just a clarifying question. Did you say that the Apache TVM optimizations were better than the heuristics-based optimizations, like more efficient, faster?
As in execution of inference time, like when a model runs.
Good question. I guess the result of the optimization, I don't know much about Apache TVM.
Sure.
Is it widely used to create better optimizations than those heuristics-based optimizations? What I'm trying to get at is there a trade-off between using Apache TVM to decrease the likelihood of these side channel attacks and creating maybe less efficient compiled?
So TVM does actually can produce better optimizations than doing it by hand. The reason it's not used is one, it's very complicated and a pain to use, and it's a nightmare to install. As anyone who's used it in here, I've talked to people, it's an awful tool to use. And two, it requires a lot of resources to find the optimizations. So you're traversing, when you find optimizations to apply, you're traversing this n-dimensional space that takes literally tens of hours to find a really good optimization for. So in AWS, if anyone's used AWS before, SageMaker has Neo, which uses TVM under the hood. So people have used it probably without knowing. But yeah, the reason it's not used is because it's a pain, it's expensive, and not that many people know about it. But it does actually produce better optimizations than by hand. Maybe not all the time, but it can do it without that much effort.
Got it. So, okay, that makes sense. Thank you.
Excellent. We have one in the Slack here. Are there any other hardware-based signals you can get which don't rely on an NVIDIA tool? For example, for other brands like Arduino?
I've not tested with them because predominantly our data center is all NVIDIA. But the original Deep Sniffer attack, about half the paper is dedicated to showing that you can do this practically by just attaching probes to a GPU. So you can do it kind of regardless of vendor. They use NCU, the tool I use to collect metrics, because it's very repeatable. There's less noise. For experimentation, it's consistent. But it can be done just with probes. It's probably a bit harder. But yeah, it wouldn't surprise me at all if we were able to find loads more of these attacks that you used. Just kind of common data. It doesn't really matter what the vendor is.
Other questions? All right, I'll ask a question. So let's say that you use your technique, do the compilation, tons and tons of times it gets well fielded. What do you think would happen if people were to train, say, some sort of ML to try and circumvent it?
I think you could probably decrease I think you could make the attack more successful again if you were able to detect that this had been done. But I also think that the space for optimizations, the dimensionality of the space that you generate optimizations for is enormous. So where I imagine an ML tool could help make the attack more effective again. But I also think the size of the space and the amount that you can move around in it is probably so massive that you would never be able to get back to the kind of success we've shown before this was used.
Excellent. Other questions? All right, then I guess I'll ask one more follow-up. So let's say that technique does give actually much better performance than you anticipate. Have you thought about ways to potentially further defend against that and make things further robust?
So TVM does actually use hardware intrinsics. So when you install like NVIDIA CUDNN, which is the toolkit for how some of these actual functions are implemented on NVIDIA hardware, I can imagine if you had a more bespoke method of generating intrinsics for the GPU, you could probably get even further away from this. Basically, as much bespokeness as you can get while it's still effective and performant is good.
Excellent. Thank you. All right, great. Let's give another round of applause.